Welcome to CS 1401 video lecture 2.1, and this is about basic concepts of algorithms. So in general, if I want to do something, I need a method by which to do it. For example, if I want to have a peanut butter and jelly sandwich, I can apply a method that fairly reliably gets me my sandwich. And I can tell other people how to solve this peanut butter and jelly sandwich building problem by providing them with my set of instructions to complete this task. So, preferably, any method for doing something, even if it's as simple as building such a sandwich, has a finite sequence of step-by-step, executable, and unambiguous instructions. That's what an algorithm is. It's finite, that is, we know that it's going to end. It's a sequence. We know what order we're going to do the instructions. It's step by step, that is, we go from instruction to instruction. Each step is executable, that is, we know how to do it. A step might be something like open the jar. We know how to execute that. Be one with the universe, maybe not so much. And finally, each step must be unambiguous. That is, each instruction must be clear as to what it is. There can't be multiple ways to do it. So let's take the example of the peanut butter and jelly sandwich. So with, as my inputs, a loaf of bread, a jar of peanut butter, and a jar of jelly, I can take 2 slices of bread from the loaf. I can put peanut butter on one slice. I can put jelly on the other slice. And then I can put one slice on the other with the peanut butter and the jelly sides facing each other, of course. Now, this method, any method that has this finite sequence of step-by-step, discrete and unambiguous instructions is called an algorithm. It has input data, like the bread and the jelly and the peanut butter. It can be expected to produce output data, like my peanut butter and jelly sandwich, and each instruction can be carried out in a finite amount of time in a deterministic way. That is, given the state we're in, we know exactly what's going to happen. There's no coin flipping involved. So algorithms turn out to be central to the notion of doing things with computers. But we have to be very careful and precise with our algorithms in order to make them useful for computers. I want to contrast a human learning to make a peanut butter and jelly sandwich with my set of instructions with a computer. So the human brings a lot of knowledge to the task. They know how to open jars. They know how to use a knife. They know how to keep the knife up so that the peanut butter does not fall on the floor, and so forth. Now, computers don't have this sort of knowledge. So we have to provide instructions at the level of detail which the computer can understand in a way that's precise and unambiguous. That's why our definition of algorithm requires a finite sequence of step-by-step, executable, and unambiguous instructions. And of course, the algorithm has to terminate, otherwise we'll be there forever. So some examples of algorithms might include calculating the body mass index like we did last time. It's a pretty simple algorithm. You take the height and you take the weight and you do some arithmetic and you get out the body mass index. Or another algorithm might be to find the shortest person in the room. Here's a method for finding the shortest person in a room. Let's line them all up at the front of the room, and we'll pick the very first person in line and take them with us. We then go to the next person in line and we ask ourselves, is that next person in line shorter than the person we have with us? If so, we'll put the formerly shortest person off on the left, back in, and we'll take that new shortest person. Then we go to the next person. If the next person isn't as short as the person we have, we'll keep the person we have. We go to the next person. If that next person is shorter, then we take them instead of the person we have, and we let the formerly shortest person go, and we keep going all the way down through the entire line. And we know that because we're comparing at each point and we always take the shortest person, that by the time we reach the end of the line, we're guaranteed to have the shortest person in the room. We could do the same thing to find the smallest number in a list, of course. If we had a list of numbers, we could basically look for we could go down the list and say, like, just take the first number, for instance, and say, is this the smallest number? Looking at the next one, we could keep going until we find, and every time we find a smaller number, that's the number we're working with, and we keep comparing numbers until at the end, we'll end up with the smallest number. That's an algorithm. It's got a finite number of steps. Each instruction is something we know how to do. Now, how to express these algorithms? So, for human beings, when we're designing algorithms, we use what's called pseudocode. It's like computer code, but not really. It's a semi-formal language that expresses the steps in the algorithm in a way that humans can understand and in a way that we can later use to translate into language that a computer can understand. The code, not the pseudocode. Pseudocode resembles a computer language, but avoids excessive detail by lapsing from time to time into ordinary English. Hey, that's a kind of abstraction, isn't it? We're getting away from the details and just thinking about the higher level concepts. So here's an example of an algorithm. Let's try drawing a 2x3 grid. And our algorithm might be something like, draw a box, draw a vertical line down the center of the box, draw a horizontal line a third of the way down, and draw another horizontal line 2/3 of the way down. Now, there are other ways to draw a 2x3 grid, but this is an algorithm. It's a sequence of step-by-step instructions. Each instruction is unambiguous, and it terminates. So it's finite, and it does produce the grid. For another example of an algorithm, let's go back to calculating body mass index. So here, if we're going to express it a little more formally, at least in pseudocode, we'd say we want to get the weight, which is going to be in pounds. We'll get the height in inches. And then we'll, using the weight and the height, calculate the body mass index, and then put that value in a place which we'll label BMI, where we can access it again. And finally, we'll take the value in that place called BMI, and we'll give that back as a result of calculating BMI. Now, that's pseudocode. For computers, we'll use a computer language, which is a formal language that has precise, unambiguous statements. We'll learn about these soon enough. In class, we'll mainly use Java, which is a computer language. At this point, we should focus on how to understand and solve problems. Later, we'll learn how to implement our algorithms in Java. So for now, we'll stick to pseudocode. Now, any language, whether it's pseudocode, Java, something else, has to have a way of representing its content symbolically. That's called its syntax. That's the form of the language. It also has to have meaning. In other words, each symbol has to have some sort of meaning, and that's called semantics. So in general, any language has both a syntax and a semantics. So when we look at our algorithm calculate BMI, we can see the syntax involves expressions like get, and then the name of the thing we're going to get, and maybe the units. It's got a way of assigning the result of a calculation to some named variable, and ways of accessing the variable. And of course, those are just syntactic things, but the semantics of it are that when it says get, it really goes out and gets the value of the weight somehow, maybe from the user. When it does the assignment, it actually takes the value that's calculated and puts it in the variable called BMI. Assigning meaning to these symbols, like the assignment symbol or words like give, that's the notion of semantics. Now, in this talk, I've discussed really informally the concept of a variable. In the next video lecture, we'll discuss more formally this idea of variable and also look at states of computation. See you soon.